In this video, we'll review how to graph linear inequalities. For y is less than and y is greater than, we're going to use a dashed line. The dashed line tells us that points on the line are not solutions. And for y is less than or equal to, or y is greater than or equal to, we'll use a solid line. The solid line tells us that points on the line are solutions. Now keep in mind, this is like previous lessons where we had single variable inequalities, where we had open point and closed point. Here, on a line, you have an infinite number of points. So you have an infinite number of closed points or an infinite number of open points, depending on whether you have the or equal. When you have or equal, points on the line are solutions, which is why you have a solid line. For the shading, we're going to look at the inequality symbol, and it's going to tell us whether to shade above or below the boundary line. It'll separate the true side, the shaded, from the untrue side or false side, which will not be shaded. Now keep in mind, the rules I'm about to show you only work when the inequality starts in slope-intercept form, when it's in the form y equals mx plus b. If it's not in that form to start with, we'll look at what to do in a moment. Now when it starts off in slope-intercept form, and you have either y is less than, or y is less than or equal to, basically some form of less than, then you're going to shade below the boundary line. When it's less than, we shade like this, or less than or equal. Here this would be a less than or equal because it's a solid line. But when you have y greater, or y greater than or equal, you're going to shade above the boundary line if it starts that way in slope-intercept form. So anytime we have greater or greater than or equal, we shade above if it starts in slope-intercept form. Now let's look at an example. Here we have y is less than negative 2x plus 3. It's in slope-intercept form, so we can look at the problem and know which way to shade. Okay, we're going to start by graphing the boundary line. We're going to separate the true side from the false side of the graph. To do this, imagine the line y equals negative 2x plus 3. That line would have a slope of negative 2, and it has a y-intercept of 0, 3. And when we draw this, it's going to be the dashed line. Now remember, it's dashed because it's just less than. So I've gone through and I've set up my graph. I've scaled the axes, put my x, y for the indications, and now I'm ready to plot the line. I'm going to start at 0, 3, and then I'm going to move by a negative 2 slope. That means I go down 2 and 1 to the right, and I'll do it again, down 2 and 1 to the right. And I'm going to draw my line. Again, keep in mind this line is dashed because it's less than. Now, because this is also an inequality, we're going to have some shading. The inequality started off with y is less than, and because it's less than, we're going to shade below the boundary line. So we're going to shade all the points that are below that diagonal line. Now, I'm pretty confident we shaded, right? But sometimes it's a good idea to check your work, especially if you're not really sure. And the way you're going to check it usually is you pick a point, usually on the true side, but it could be on the false side. You pick a point and you test whether it's correct. If it's on the true side, when you substitute it in, it should work. If you pick something that's on the false side when you plug it in, it shouldn't work. And that's every bit of valid to check. If you pick a point that's on the non-shaded side, substitute it, and it gives you a false statement, then you know that you picked a point that is not on the shaded side, and it didn't work in the equality, which means your shading is probably correct. So let's pick a point on the shaded side, though. Let's pick a point that's really easy to find. Let's test 0, 0. Now 0, 0 is on the shaded side. If I test it in inequality, it has to work out. Because we shaded it, 0, 0 should be in the solution. So let's test it. We'll take our original problem, y is less than negative 2x plus 3, and we'll substitute 0 for x and y. Negative 2 times 0 is 0, and 0 plus 3 is 3. So we get 0 is less than 3. Now we're going to ask ourselves, is 0 less than 3? And it absolutely is. This is a true statement. And because it was on the side that shaded, it should be a true statement, which means our shading is probably correct. We picked a point on the shaded side, and it actually works out. It's a good indication to let us know that our shading is correct. Now let's take another example. Here we have y is greater than or equal to 3x minus 1. We're going to graph the boundary line, keeping in mind that this time, because it's y is greater than or equal, the or equal tells me we have a solid line. The slope is 3, and the y-intercept is 0, negative 1. I've labeled and scaled my axes, and I've plotted 0, negative 1. Start with the y-intercept. Now we're going to move by a slope with positive 3. This means from the y-intercept we'll go up 3 and 1 to the right. Up 3 again, and 1 more to the right will give us a third point. When we graph this boundary line, it's solid. Again, because it was greater than or equal. Now for shading, we had greater than or equal, which means now we're going to shade above. Greater than means above. And to confirm, I'm going to pick a point. Now 0, 0 is in the shaded region. It is above the line, just barely. So if I test 0, 0, it should work out to be true because it's part of my shaded solution. So let's check it. 3 times 0 is 0, and 0 minus 1 is negative 1. I get 0 is greater than or equal to negative 1, and 0 is greater than any negative number. So this is a true statement, and it confirms my shading. We picked a point on the shaded region, it checked out in the inequality, my shading's correct. Let's check one more here. Here we have y is greater than 1/2 x plus 2. This time we have the boundary line that is dashed. We know it's dashed because it's just greater than. The boundary line has a slope of 1/2 and a y-intercept of 0, positive 2. So I've labeled and scaled my axes, and I'm going to start by plotting that y-intercept, 0, 2. The slope is 1/2, so from that y-intercept we go up 1 and 2 to the right. Up 1 again, and 2 more to the right gives me that third point. And this is a dashed boundary line because it was only greater. Now the symbol for shading is going to be greater. This means we're going to go and shade above. So if we shade above the boundary line, and then I'm going to test a point. Now notice this time 0, 0 is not in my shaded solution. Now I can still test that point, or I can pick any other point in the shaded region and test that one. If I pick a point in the shaded region, for instance 0, 4, it should work out to be correct. If I pick 0, 0, which is not in the solution set, then I should suspect that it's not going to work in the inequality. So let's check it. And again, you don't have to pick a point in the shaded region. If you pick a point that's not in the shaded region, just got to make sure that when you check it, it comes out to be false. So here we go. If I plug in 0, 0, I get 0 is greater than 1/2 of 0 plus 2. Half of 0 is 0, and 0 plus 2 is 2. Now is 0 greater than 2? No, that's wrong. 2 is greater than 0. This is false. But that doesn't mean we did the problem wrong. It just means that 0, 0 should not be part of the solution. We tested in the inequality, it doesn't work, which means the side that has 0, 0 should not be shaded. Look at our graph. Did we shade the side with 0, 0? No, we didn't, which means our shading is correct. We shaded the side where 0, 0 was not because 0, 0 is not part of this shaded solution. Either the side works or it doesn't. If you test it and it doesn't, then it shouldn't be the shaded side. Shade the other side. All right, so what if the problem doesn't start in slope-intercept form? What do we do then? What if, for example, we have 2x minus 3y is less than 9? This is not in slope-intercept form, this is standard form. What do we do? Well, we're probably going to go ahead and put it in slope-intercept form. We're going to get y by itself. Now remember, when we solved inequalities, we had some times when we had to flip the symbols. Let's review the rules for when we do it with linear inequalities. We're going to need to reverse the symbol anytime we perform an operation that makes the opposite, such as if we divide both sides by a negative. If we divide both sides by a negative, we reverse the symbol. Or if we multiply both sides of the inequality by a negative, we reverse the symbol. And the third rule is if we have to rewrite it because y was on the wrong side. If we have to rewrite it to get y on the left-hand side, we reverse the symbol. So 3 times we have to worry about reversing the symbols. Multiplying or dividing both sides by negative, or if y is on the wrong side. So don't forget these rules because it'll make the difference between having the correct solution shaded and the wrong one shaded. Alright, let's go back to that example. 2x minus 3y is less than 9. Do you think we're going to need to reverse the symbol? Well, I see y is negative, and when I divide by that negative 3, I'm probably going to have to reverse. So let's go through it. We're going to go and start by trying to get the negative 3y by itself. To do that, we'll move the 2x to the other side. Here we have a positive 2x, so we'll subtract 2x to get y by itself. This leaves us negative 3y is less than negative 2x plus 9. To fully isolate the y, we're now going to divide both sides by negative 3. So that means all 3 pieces get divided by negative 3. And because we're dividing by a negative, we'll reverse the symbol. Now we have y is greater than. Negative 2 divided by negative 3 is positive 2/3, so we get 2/3 x. And 9 divided by negative 3 is negative 3, so we get y is greater than 2/3 x minus 3. Let's go ahead and graph this. Well, the slope of the dividing line is going to be 2/3, and it has a y-intercept of 0, negative 3. So we've labeled and scaled a set of axes, and let's plot the line. Starting at 0, negative 3, and then moving with the slope of 2/3. Go up 2 and over 3 to the right. Or we could go down 2, but then have to go 3 to the left. It is a dashed line because we do not have or equal. And now we need to shade. We can't look at the original problem. We're going to look at the new one when we got slope-intercept form, that y is greater than 2/3 x minus 3. The inequality is greater now, which means we're going to shade above. And it's probably a good idea, really, when it's not in slope-intercept form to start with, to test a point. So let's check 0, 0. I'm going to test it back into the original problem. I want to do this because if I made a mistake, I wouldn't see it necessarily in that new problem. So always check in the original. 2 times 0 is 0. 3 times 0 is 0. I get 0 minus 0, which is 0, is less than 9. 0 is less than 9, which means that's a true statement, which means 0, 0 should be shaded. And if we look at our problem, that's what we did. We shaded the half that had 0, 0. Well, here's 2 more examples. Why don't you go ahead and pause the video, work these 2 out, and then resume the video when you're ready to check your solutions. I'll give you a moment. All right, hopefully you've had a chance to work these out. For example number 1, we've got x's on both sides. We want to get the y by itself and isolate the variable, so we'll subtract 3x from both sides. 2y is now less than or equal to negative x minus 3x, which is negative 4x, plus 2. Dividing both sides by 2, which is a positive 2, we will not reverse the symbol, we get y is less than or equal to still negative 2x plus 1. The slope is negative 2, and the y-intercept is 0, 1. Starting at 0, 1, going down 2 and 1 to the right, down 2 and 1 to the right again, and then we're going to draw the dividing line, which in this case is solid because it's less than or equal to. The new problem is less than or equal to still, so we'll shade below. And if I check it back into the original problem, x and y are zeros, if I test 0, 0, and I get 0 is less than or equal to 2. 0 is smaller than or equal to 2, which is a true statement. 0, 0 should be shaded, and if we look at our problem, that's what we did. We shaded where 0, 0 is, so our shading is probably correct. For example 2, we're going to have to start by subtracting 4 from both sides. That leaves me negative 2y is less than 6x. Now, negative 4 minus 4 is negative 8. To finish, we're going to divide both sides by negative 2, and because we're dividing by negative, we're going to reverse the symbol. We now get y is greater than negative 3x plus 4. For the dividing line, the slope is negative 3, and the y-intercept is 0, 4. Starting at 0, 4, going down 3 and 1 to the right, and down 3 and 1 to the right again, and drawing a dashed line because it's just greater than now. Greater than, because of that new symbol, tells me we should be shading above. Now let's test a point and make sure we did it correct. We can pick a point on the shaded side, or we can still test 0, 0 because it's easy to spot. 0, 0 is not in the shaded solution, which means if we test it, it shouldn't work. So let's check it. X is 0 and y is 0. 4 minus 2 times 0 becomes 4 minus 0, or just 4. 6 times 0 on the other side is 0, and 0 minus 4 is negative 4. I get 4 is less than negative 4. And that's wrong. 4 is greater than negative 4. So this is a false statement. Now because it's a false statement, that says that the point 0, 0 should not be shaded, and if we look at what we did in the problem, we didn't shade. So we got the correct side shaded because we did the other side, the side that doesn't have 0, 0. So again, this confirms what we did with our work. Alright, thank you for watching this video, and hopefully it helps you understand how to graph linear inequalities.